Does anyone else have any problems signing into RStudio Cloud?
Yeah.
It kept saying like your password is valid. I changed my password like 7 times, so getting a link.
RStudio Cloud?
Yeah, and like would get a link to change it. Eventually I pasted it into Excel. So I'm like copy paste, make sure this is the exact password, and then get back with the password is not correct.
This is great.
So it seems like there's something wrong with it at the moment.
Okay.
Yeah.
This is Slack.
Something different. I wasn't like, oh, this is
Is this the only email? Yeah, no, there was a link though.
Yes.
All right. I'd like to go ahead and get started. We have a little bit of information to cover today, and I just want to take a few minutes at the beginning to do some introductions to give you a sense of a roadmap of where we're going over the next 5 days. If you're having some problems signing into RStudio Cloud, that's not a deal breaker at this exact moment, so we can continue to work through it. The plan for today is going to be to spend maybe 30 minutes or so at the front end to lay the groundwork and to try to let you know where we're going, what we want to accomplish, why we're here, and then we'll spend some time thinking about or learning about R and teaching you some of the fundamentals of the language. And towards the latter part of our time together today, we will spend time in RStudio Cloud. So you've got at least 30 minutes, and Ali and Akshay can sort of help you guys while we're going through some of this material. So just as a very brief introduction, my name is Matt Hershey. I'm one of the faculty members here. I run a lab down the hall for those of you who aren't located in this building. And just again, a very brief introduction. I was a chemist once upon a time. I made semiconductors and tried to put them into bacteria to do all sorts of crazy things with them. It was a very biomaterials-inspired graduate work that I did. Then I ended up in a postdoc looking at metabolism, serendipitously. And finally, when I came here, my lab studies all things metabolism. And you're already asking yourselves, well, why is he up here going to teach us something about data science and bioinformatics and computer programming? Tim is nodding vigorously. And the reason is because a few years ago, I said to myself, really, we need better workflows to analyze our own data. We, in my lab, do enough work to generate sort of omics scale data, proteomics and metabolomics, and we need better workflows to analyze those. Now, that's nothing to take away from our fantastic collaborators or to take away anything from the computational biology resources on campus or even the core facility. But there was a point of time when I said, well, we are doing this enough that we need to invest in it ourselves. And so a few years ago, I decided to take the dive into R and to learn the R programming language. And this was around the time that some of these new tools in data science were being discovered and talked about and used for discovery. And then the way that I'd like to describe it is something miraculous happened, something quite surprising happened. I was working on a project, and I was docking with a couple of the undergrads in the lab. And we started thinking about some ideas for one of them to use for the summer to interrogate over a summer project. And I realized as we were working through this that I started thinking about projects differently. And it was at that period of time I realized that learning some of the fundamental tools and concepts in data science and being able to apply those to publicly available data allows us to come up with better hypotheses. So far beyond just generating a workflow to go from raw data into figures in a published report, now one of the things I'm most excited about is having the ability to generate data for a hypothesis, for a project, before you even start that project. And so one of my goals now for you all is to be able to teach you some of these fundamental skills so that by the end of this week, you'll be able to take a data set, analyze it, generate some figures, and then I hope you all will make time next Tuesday. We have a speaker seminar here Tuesday at 4, but I thought that we would take a couple of hours from 2 o'clock to 4 o'clock next Tuesday to go through and give some very short, maybe 2 to 3 minute final presentations of what you learned. So the goal is to take an hour and a half today and for the next 4 days in this week is to take a rapid fire, sort of fire hose approach to teaching you everything that I know about data science and how we can use this to interrogate data sets, and then have you then teach all of us on Tuesday what you learned. So that's the overall goal. Any burning questions before we get started? Besides, is this going to actually work? Okay, so welcome to Tidybiology. This is the molecular physiology edition. This is an introduction, a zero-entry introduction into what we're calling biological data science in R. And so I want to start by showing you a picture of a school bus, but I want to start with a very short anecdote that I heard Dave Piston at WashU tell. He's a biophysicist and microscopist. And it was a fantastic story that I think captures so many of the challenges in molecular biology. So the story goes, there's a young alien on a distant planet with a high-powered microscope. And this young alien is peering down through the microscope onto planet Earth, and the alien sees what they think is a yellow school bus. All right, so these yellow school buses from the distant planet appear to have this regular behavior. And so all of the school buses are tightly clustered, and then all of a sudden, 2 times a day, the school buses disperse. And so he watches it the next day, and again, 2 times during that day, all of the school buses disperse, and then they come back together. And so the young alien is really excited, and he coins a new term, sort of sudden bus dissociation. Okay, and he is going to write this up and share it with everybody that he knows. But then all of a sudden, he's watching and watching, and then all of a sudden, it doesn't happen that day. And the young alien is crushed, right? What happened to this term that the alien coined? And waits another day, nothing happens. The third day, finally, the buses start dissipating again. Okay, so relieved, everything looks again regular, and so on, until a few weeks later, the buses stopped ceasing altogether. And so, of course, we know that this is a story about sort of the regularity of school buses and the weekends and the summer breaks and these sorts of things. But the point that Dave was making when he told the story is how do you know whether you should be paying attention to the major event that you see or these sort of flickers of the yellow school buses around the periphery, right, as a microscopist? But I like this story because it questions, I think, more deeply, how do we know what we know? And this will not be a philosophy class, but if you were the alien on that distant planet, then you would say, well, how do you know the thing you're looking at is like the most important thing that yellow school bus does, or is it just some tangential behavior? And so that leads to like a bigger question. When you're thinking about science and you're thinking about a hypothesis and you're thinking about something to test, like how do you know if it's a good scientific idea? Like how do you know if you're going to be looking at something that is this dispersion of yellow signal, or whether you want to be looking at what's happening when that's dispersed? So what would you say? This is a poll. I've asked like 3 people, and I'll ask like 30 en masse. If you don't know anything about, let's say, a gene, what do? What's your favorite approach? Right? You end up with a gene list. And the number 1 gene on your gene list that you think is most important for your biology is a gene, a Riken cDNA. What do? Paul, what do you do?
CRISPR.
Okay. Tim?
Overexpress it.
Overexpress it? All right. Matt, what do you do? Google. All right, what does my gene do? Clever. Anyone else?
Skip it and go back to GLP-1.
Go down the list until you find something you recognize. Okay. All right. Well, this is actually, it's interesting that Matt said Google, because does anybody know who this is? This is Richard Feynman. This is, let's see, not going to play. Okay, so Richard Feynman, famous physicist, Nobel laureate, worked on the Manhattan Project, essentially solved some of Einstein's unsolvable problems. And it's interesting because he talks in this muted audio clip about the difference between knowing something and knowing the name of something. And so he goes through and he says, okay, this is a brown-throated thrush, and in Chinese we call it this, and in Portuguese we call it that. And his father told him really young, is if you know the name of something, you still don't know anything about that bird. You just know something about the people and what they call that bird. And I like this because in science we have names for things. We have to have names for things because we have to communicate them, right? But like the sudden bus dissipation, for example. But it doesn't really tell us anything about, necessarily tell us anything about what that thing does. Okay? So of course, when we want to sort of come up with an idea or sort of test an idea, we follow the scientific method, right? So first, we define a question. Second, we observe, maybe gather some information, think, go to Google. All right? And then finally, we form a hypothesis. And then we test the hypothesis. So we perform this experiment, right? This is pretty standard stuff. And now you're really questioning like your decision on how you spent your time today. Why is Matt standing up in front of us telling us about the scientific method? I mean, you do these things all the time. You test your hypothesis, you analyze the data. We have this slightly convoluted way of trying to disprove the null hypothesis. And then we sort of ask the question, do we reject this or not? And finally, we interpret the data, and if we're lucky, we then have some more questions, we form a new hypothesis, and we repeat this. But the problem is, I think, I'm pretty convinced that we, being people, are just not very good at coming up with ideas. And so this is part of what's driving me now, is this desire to try to come up with better scientific ideas. Now, this is not going to be a boot camp on how to come up with a good scientific idea. Maybe that will be next week. This week is going to be a boot camp on how to use some tools in order to interpret data, to draw conclusions, to come up with better ideas. It's interesting, though, because there's a new type of science that's happening now, though. This is cute and quaint, maybe slightly antiquated, where the questions were simple and the unknown was sort of obvious, perhaps in front of us. But now we have much more sophisticated techniques in order to collect data, right? We collect more data than we've ever collected before. And so here's just a very simple schematic of we can screen microbiomes, metabolomes, proteomes, transcriptomes, epigenomes, and so on. And so oftentimes when we do these screens, this now sort of comes in at the level of observe. We gather information and think. The unspoken and sometimes spoken joke is that if you don't know what to do, we do a screen, right? And we've got Matt Foster here from the Proteomics Core Facility. We've got Paul Grimsrud here in the DMPI Proteomics group, and we've got sort of some pretty hardcore screeners. And so, but this is really just a step to observe and gather information in order to try to learn something about this. And so it's sort of within this context, this is my goal for you, to try to teach you some of the computational tools to take data, to insert yourself into analyzing the data, interpreting the data, drawing conclusions, and perhaps even getting to the point where we can gather information before doing an experiment to validate our hypotheses. Okay, because this really is how most people and how I am thinking about this hierarchy of knowledge. we gather information, or we gather data, we sort of assimilate that into some information. We do this a few more times, we can take this information, and finally this becomes knowledge. And if we're lucky and we're around long enough, that this knowledge then becomes wisdom that we can use for some type of outcome. Okay, so what ends up happening now, though, is that there's, again, some new tools that allow us to take data, because, like I said, data is bigger and more complicated and more sophisticated than ever before. And so we have now a new set of tools that allow us to go from this data to information step. So what does that look like? Well, I call this new and emerging field of data science because you can see that at Duke we have a focus through the School of Medicine and Department of Medicine on data science. You can see that the university has several data science initiatives. So what is this exactly? Well, this is one of the first attempts to try to crystallize what data science is, but this is quite old in terms of data science. It's nearly 5 years old. But one of the first attempts to define data science was some combination of math and statistics knowledge with some sort of overlay of some hacking, sort of computer hacking-ish type skills, with some sort of substantive domain expertise. And it's sort of in this, this sort of simple Venn diagram that we end up with this combination of abilities to take data, to hack together some information about it that is specific for your expertise area. Okay, so this is the very first sort of summary of this. Now we could say some machine learning, we've got some hacking skills, maybe taking out some substantive expertise, math and statistics knowledge. Our traditional research is perhaps in the area there to the right. Data science there is perhaps in the middle. Okay, so this is a slightly updated one. This is a few years later. There have been like thousands now of Venn diagrams of data science, so you can take a moment and look at this. And so the graduate students are sort of snickering because you can see your graduate school office mate is there, the thesis advisor absolutely right there, and then the probably the best one though is the outside committee member, right? So pure evil with a little bit of math and stats knowledge, right? So I highlight this though because this is a fluid and growing definition and a fluid and growing field. And so people are even questioning, will what we call data science still be called data science in 5 years from now? I don't know. I won't make any predictions, right? But the point is to appreciate that there's this emerging both need and emerging tool set that allows people with some hacking skills, i.e. some computational and data literacy, some knowledge of math and statistics, right? Because if you don't have any knowledge of stats, then you're going to be doing things wrong all the time, and some sort of substantive expertise. Well, I think we all fill in that, especially in this room, we all fill in that bin quite easily. So there's this idea of data science. It's this amalgamation of these different things. But the whole point then that I'm going to impress upon you of the why data science and why you are here is really to try to take data and to turn it into knowledge. And the last quote that I'll show you from today is from Isaac Newton, where I think Isaac Newton quite humbly said, "I don't know what I may seem to the world, but to myself I've only been like a boy playing on the seashore and diverting myself now and then finding a smoother petal or prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me." And I like that because as a scientist, that's what we are, right? We're looking at these shiny pebbles, trying to understand these biological truths. And today I'm going to try to start you on the journey in order to gain a skill set to try to get there. Okay. Now, there are several approaches in data science, and Stack Overflow, which we'll talk about a little bit more, has a survey every year to try to ask computer programmers sort of the language of popularity through the years. In the animated version of this is sort of one of these bar graph horse races where you can see the change in the languages, because some of you might say, well, why R? and why not Python, or why not Java, or why not SPSS, or why not any of these other languages, right? And I would say, well, why not Excel? Right? If we look at the world's most popular programming language, right? Like everybody's quite in the weeds. So we'll do another informal survey here. Show of hands. Who knows how to write a single line of code in Excel to take the sum of, let's say, a row of cells? Yes? No? Okay, right. So who knows how to do the same thing in R? Okay, the TAs. A couple of people. Okay, so right, like there's this major disconnect. But the point is not why not all of these other things. The point is, well, why not start with one that allows you to start this journey, and then you can figure out for yourself if this is the most efficient, if this is the most intuitive, and so on. But then also, quite practically, why am I not standing up here teaching you Python? Because I have no idea how. Right? Because a couple of years ago, I decided that I was going to dive into R. Some of the tools and libraries were available that you'll be learning today and through the next couple of days this week. And so this was an opportunity just to dive in, to try it, and to start. And perhaps next year, I'll stand up here and teach you a Python boot camp. But the point is, it doesn't really matter. It's a little bit like that question that I just asked you. If you didn't know anything about your favorite gene, what would you do? And it turns out universally the answer is going to be dependent upon who answers it. So the proteomics person, to my surprise, did not say proteomics. Oh, you missed that one. And so, right, but the biochemist is going to say, well, I'm going to clone and overexpress it and test its activity. And the geneticist will say, oh, well, I'll make a yeast mutant and I will sort of screen for its growth. And the mouse physiologist will say, well, I'll make a knockout mouse and I'll feed it a high-fat diet and look at its phenotype, right? So the point is it depends. But any one of those could tell you something about your favorite gene. And if I asked you, well, which is the better approach? Well, it's the approach that allows you to learn something fundamental about the gene you're interested in. And that's the exact point I want you to take away here. The best programming language is the one that's going to be able to allow you to do the things that you want to do to achieve your goals. It's that simple. Okay, so now we're going to dive into R. So R is a programming language. It's cleverly named based on its predecessor, which unintuitively was S, but go figure, so it's called R. But R is a programming language that is going to be the basis for everything that we're going to do together in class. And another sort of quick poll, who speaks a language in here other than English? Raise them high, be proud. Okay, so the rest of you by the end of this class should all be able to raise your hands because now or soon you will be able to speak R. Okay, R is a language, just like any other language. All right, this language is going to be a little bit unfamiliar at first, but you will learn the language and then you will be able to order a burrito in R, or you will be able to ask for a beer or whatever it is, right? You will know enough in order to get around within this language. Okay, so the first thing, R has values. So there's a lot of different types of values it can have, but it has values. So 1 is a value, floor is a value, date there is a value. It also has objects. Okay, in this case, an object is X. We'll talk about that little funny character that kind of looks like an arrow pointing to the left in a moment. All right, but the difference between a value and an object is going to be incredibly important. So an object here is a name without quotes, followed by something that looks a little bit like an arrow. And then what you can do is you can basically store anything inside of an object. All right, so an object is really just a container. It's an empty container, and it can store a lot of different types of things. It can store values, but it also can store some other things, and we'll get into that. Right, so value, object, function, result, etc. But understanding the basic structure of how R is set up will be important. So you've got a value, you can assign that value to an object, you can store that object. Now, you can also have an object that has multiple values inside of it. And so the way that you do this is with C. So you can combine or concatenate or anything that's sort of intuitive for you to remember that you combine all of these together. I should mention, I'll show you a little bit later, but all the slides are sort of available to you. There's a folder within the RStudio Cloud, a project that says slides, and this is, so if some of you, if you like following along, or some of you, if you like sort of taking notes on slides, that's available to you. I'll show you where it is when we get into RStudio. Okay, so objects, single object or multiple objects. R also has functions. So function is going to be a specific operation that you do to an object or a value. Okay? So a function here is going to be a name, also without quotes, and some of these semantics will become important. So it's a name without quotes, but it's followed by a parentheses, and the parentheses tells it what it's going to do to the objects. Okay? So values, objects, functions. We'll spend some more time with this. Sometimes functions can have more arguments or more sort of specifics. So if you are going to take a wild guess of what this function does, what would you say? What is it?
Keeps 3 digits.
Yeah, it keeps 3 digits. It's going to round, okay? And how many, sort of how many digits it's going to round to? In this case, 3. Any guesses on what it's going to round? X. Yeah, exactly. So it rounds X to 3 digits. So that's a simple function. Okay, pop quiz. Which of these are numbers? All right, that's a number, right? Number 1. What about the next one? Yes, no? Show of hands. Yes, it is. Show of hands. No, it's not. Okay. No, those are not numbers. Because if they're in quotes, then they're called something, there's something called a string. All right, string is a word. You can store words a lot of different ways. Okay, but the quote's going to be a special where you're going to have something that's a word. What about the last one? Number or not? It's not in quotes. No. Why not? What would it be instead? You're right, it's not a number. It's an object. Yeah, exactly. And the object could store a value, absolutely. But in this case, it's an object. Okay. Suppose now that we assign 1 to ONE. Okay? So again, we're going to follow that left-hand arrow. So now the object 1 is going to store the number 1. So which one of these will work? All right. Well, they say, raise your hand if you think it's going to work. The first example. The second example. Third example. Fourth example. You guys are good. All right? I think most people agreed. Because your object can store a value, and you can perform a log transformation on a value, or you can just perform that on the value itself. Okay. Now, data. Data in R are stored in tables and data frames. All right? This should look really familiar. I asked you who's sort of comfortable enough in Excel. This looks like Excel, right? You've got columns, you've got rows, we've got some column IDs there. Our row IDs in this case is just the row number. So the data, though, are stored in DataFrame. It's conceptually equivalent to a spreadsheet with rows and columns. So this is a data set that you'll see a little bit more. This is called chromosome. All right, and so we have an ID, which is just going to be our chromosome number. And then we have some information about that chromosome, the length of the chromosome, number of base pairs, variations, protein coding genes, pseudogenes, et cetera, et cetera. So we can think about this like an Excel spreadsheet. We can actually call a single part of the data frame as well. So we do this by chromosome and then that money sign ID. So now what we're doing is we're just going to select out one of these elements of our Excel spreadsheet. So it'd be the same as you click on this column, you select the whole column. This is the equivalent to that. Okay. And you can also save it as an object for later use. So now I just want my IDs and I want to store that because I want to do something special with it. And so again, I'm going to take this left-handed arrow. I'm now going to say my object is going to be chromosome ID. And so now instead of writing chromosome ID every time, I can just write IDs and I can do other things to it. So inevitably, what will happen is you'll be working through maybe some analysis, and you're going to be saving all of these intermediate objects. And at the end of it, you're going to look at your environment, And it's going to be like chock full of 50 different things that you called IDs, and then you called another thing, and then you called IDs. Hopefully you don't end up with like IDs final, and these things, right? But what will happen is as you get a little bit more familiar with this, you will find that there are some things you absolutely want to save, some intermediate objects, and then some you can just sort of breeze right through them if they are intermediate to an analysis that you're doing. And so there's no right answer for when should I store my my sort of set of values as an object. That's something that you will decide. Okay. Now, there's something that's called an integrated developer environment, IDE. This is a common term across most computer programming sort of development environments where we can interact with R directly, just like we can interact with just about any programming language directly. But there are different pieces of software that allow us to interact with it more efficiently. And R's version of their integrated developer environment is called RStudio. So R is the statistical programming language. This is which has the values and the objects and the key features that I just told you about. RStudio, this integrated developer environment, this is R sort of underlying it, but it has several features that allow you to work with it quite easily. So if any of you are familiar with Python, then something conceptually similar would be the Jupyter Notebooks. So Jupyter Notebooks is one integrated developer environment for Python. RStudio is one integrated developer environment for R. Now I think most people would prefer to use some integrated developer environment because it makes complicated tasks much easier. And one simple way to think about this, the relationship between the two, is that R is the engine and RStudio is sort of the driver's seat and the console and the buttons and knobs and radio and like all of these things that enhance the experience. Like you don't need all of that stuff to drive the car. Well, maybe the steering wheel, but like for the most part, right, you have the engine and the engine goes. But you have all of these other things that enhance the experience and make it easier for you to drive and do the things that you want to do. And that's exactly the difference between these IDEs. Okay, so now if you have access to RStudio, let's go ahead and into the a quick demo. Okay, so what you should do is, does anybody not see this screen yet? Okay, Ali and Akshay can cruise around and help if you don't see this yet. All right, if you do see this, what I want you to do is to click on DMPI. Learning is if you want, you can check out Learning sometime. This was, I taught this course for graduate students earlier this fall. That was their version of it. We've enhanced and added a couple of data sets. So you can click on DMPI, and it's going to open up a project. So a quick tutorial, a quick intro to RStudio Cloud. RStudio Cloud is a cloud-based version of the RStudio developer environment run in the cloud that RStudio is allowing us to use for our class. This is like alpha software. Like anyone should be able to sign up for an account, but as far as running classes, not everyone does this. So this is what you should see. What they have here is an exact environment of RStudio. That's here. And then a couple of other things. They've got some guides, learning, primary, what new. In spaces, you have your workspace. Then this is a workspace I've generated just for this class. And within the workspace is a project that's called DMPI. If up here, where my mouse is sort of going around, if you see something that says save this as a project, go ahead and do that. So you can save your own version. What that's going to do is it's going to copy it over. If you don't see that, that's fine. You should have your own version already. All right. So now what you have is your own version that you can that you can break, you can reset, you can re-download, etc. So so this is RStudio Cloud, and if we look at is that the right project? If we look here, this is RStudio. So we see something that is absolutely equivalent, where we've got, again, I'll just show you the quick sort of tour of this. where we've got a console, we've got a terminal. I'll come back here and show you. We've got the console, so this is the R console. And we've got a terminal. Both of these are here. So what I want you to do is I want you to go to 1 and open demo. Okay, so now we have a file. This file is an R Markdown document, RMD. So we open it, and that's what we see here. If we come and we open up, the R programming language, we see something like this. Now, if I say 1 plus, actually it's just loading, we can interact with R directly, just like I showed you. So we'll let this finish loading.
And Matt,
Yeah.
I think some of us are looking at things that didn't include those 3 files, but we have like 6 different files in the file menu, and demo is not one.
Did you hit intro? Hit number 1, which is intro, and then demo.
Yeah, so the question was about where to exactly find the files.
Okay.
So if you come here, you'll see several folders.
Yeah.
If you click on one intro,
Okay. Thank you.
you'll find it there. All right, so let me just show you. So this is R, right? So we can do simple operations. So 1 plus 1. We can do more complicated operations where we can do things like this. 10 times 1 times 2 times 3. We can take 3 different objects and we can perform a single operation to them. We can also store an object, right? So we'll say this is Tim, and Tim's what? Tim's 100, right? So then we're going to say 10 times Tim is 1,000, okay? So this is R, right? We can do everything that we want to or that we need to in there. But we can also do that here if we want to. We can come down to the console and we can interact with it just like that, 10 times 10, okay? Now, the nice thing about this, though, is we can also interact with what's called an R Markdown document. And so this R Markdown document is going to allow you to write code and notes about your code, sort of intermingle them in a meaningful way. So if I just sort of run this code, 10 times 1 is 10, 10 times 2 is 20, 10 times 2 is 30, and so on. It's just like it was in the interacting with R directly. I can run this here, okay? So this is an R Markdown document that lives here when we open it. We have a console right here, so I can interact with R directly if I want to. Over on this side, this is my environment, right? So if I come back down here and I assign a value to Tim, right? Now Tim is a value, Tim is an object in my environment. His value is 100, okay? So I can see what things I have in my environment. And then down here is a file viewer. So if you look at pre-class, again, I taught this course for graduate students this fall, and so some of the material is going to be directly relevant to them. I tried to clean it up to make it specific for you guys, but I sent out some install instructions. Those are here. The workshop email that I sent you, that's here. The syllabus is from the former class, but it gives you a sense of where we're going. Here's the intro class, so we're going to have 5 classes together. What you'll see here is directories 1 through 5. So all of our course materials for today are in here, tomorrow in here, and so on. And then you don't need to worry about these so much, except for this last one. If you click on it, you'll see here's the slides for today's talk and the talks for the rest of the week. Okay? So we're all here, and we're all in this sort of demo. And you can see that if you take this and you cut and paste it down to here, that you can run some of this. It should totally run. Now, if you try to run this, right, I said x is x times 10. This should work. Okay? This is going to give me my 10 times 1, 2, and 3. If I run this, we should get an error. We say x times 10, non-numeric argument to binary operator. Now, for the most part, I find R's error messages incredibly unhelpful. But in this case, we actually do have some sense of non-numeric argument. So here, x in quotes is non-numeric, right? So it's a string. So what we're trying to do is it says you can't take something that's not a number and then perform some binary sort of operation on it. But really what that means is you can't multiply a letter x or a string by the number 10. Okay? So this is the R Studio integrated developer environment. Now, let me show you a couple more things, and then I'll ask you to try a few things on your own. I want to tell you a little bit more about R Markdown. So this was part of the reason that I sort of decided to, and that I dove into R as my first step in this data science journey. Before we go into some of the specifics, I want you guys actually to start and go ahead and do this now. So if you go to that folder, now open up another R Markdown document called 01_exercise. I want you to read through the file and do everything that it tells you. So we're going to go ahead and take 5 minutes. Shoot your hand up if you have any questions. And we'll be happy to help.
Oh, yeah.
Just log into the Slack channel. Do you have the email that I sent you? But that's weird.
Install instructions. So if you scroll up or down, I mean, no, go back to the message. Okay, and then let's see. Okay, yeah, just go. Okay, and then, yeah, did you type in?
Yeah. Oh, I type this one.
Okay.
That's wrong. Should be no.
Yeah, it's asking you to like. Yeah, circle back. You don't want to create a channel. That's right. No, you don't want to do that.
Oh, really?
You don't want to do that. Try to go back. First, find your workspace. Let's see. Nope. Save it. Continue.
This one.
So then, show. Okay, so can I drive for a second?
Sure. This is very. Oh, you want to copy it?
Yeah.
I think because this is preview in the email, so maybe.
Join us like Tidybiology. Do you have a Duke account?
Yes.
Okay, use your Duke account.
Okay.
Because the Duke account, I made it so that everybody has a Duke account.
Great.
Yeah, it's like, okay. Just go.
So this is created. What's the
You're creating an account. So just this is going to be your account to sign into our Tidybiology. So.
Oh, okay. So what's next?
Okay, now go to help. And then click on here. So it needs like this like key. So now, did you ever have an RStudio account or no?
I'd log with.
Okay.
There's two join signs.
Okay.
Should go to.
Now, I'll go to projects. Let's see, so. Okay. I'm just gonna create some code. And then what you can do is you can go to 0, 1, and exercises are. Okay.
Thank you so much.
We'll take another minute or two and finish that R markdown.
I do know Tidybiology, so that's what comes next. But now that the instructions next, I turn back to type library. Can't jump.
I was just curious because I was like, I think that's on the list.
All right, go ahead and finish that up. If you continue looking intently at your screens, I'll think that you're still working. If you like whip out your phone or something, that would be a cue to like let me know that you're done. All right, we'll continue along. So that's our markdown. Thanks for coming. No, so that's our markdown. Our markdown is it's its own markdown is its own language. It's a way to format text. Our markdown, in this case, this R markdown document, is a way for us, like I said, to intersperse some code. So we have here a code chunk. The code chunk can be run, and then we get a resulting code. So this is something that you guys just did. You click on that little green arrow, the code chunk runs, and then you get the result right underneath it. So now you can start to envision what some analysis looks like, where you have some text that's written in Markdown, and you've got like some headers, or you've got some formatted code, maybe some bullet points, some notes about what you're about to do, and then the code. And then you run the code and you see the results. And then maybe some analysis of it, which suggests that maybe I should do this. So then you do some more code and some analysis and so on. So it's this way now that you can start to see into the future of, I've got some data and I do a little bit and then I make some decisions about those data and then I decide to go left, and so I went left, and then I write some code and so on, and then I decide to go right, and then right. So you've got these decision trees, and this is the way now that you can envision interspersing your ideas with the data analysis. All right, now I want to introduce you to something called packages. So within R, we've got something called base R. And base R has several functions that are available for you to use. So base R is the R programming language. We've got functions like mean, and we've got functions that will do much more complicated and sophisticated things. We can sample from a data set. We can perform some pretty complicated and above my pay grade levels of statistics. Right? R was designated and designed as a statistical programming language. And within this base R, we've also got some data sets. We've also got some help pages and so on. But the nice thing about R is there's an entire ecosystem, an entire community who's developed several other what we call R packages that have functions. So let's say you wanted to do some transformation, let's say principal component analysis, something we oftentimes do looking at omics data. And we want to say, well, let's reduce our dimensionality and look for the primary drivers of the variation in our signal. Well, if you were a little bit sadistic and maybe crazy, you would try to write this from scratch. But in R, what we can do is we can leverage the fact that several good packages for such an analysis exist. So we can find those packages and we can use them, and we can then perform some of these analyses. So packages, again, have functions. Packages have data. Packages have some help and documentation along with them. All right, so what exactly is a function? I introduced this idea. Function is one of the key things within R. We've got values and objects and functions. But the way to think about functions is verbs. A function says, do this, and then we have parentheses, to that. Okay? Sometimes these functions, we called them arguments before, but sometimes we have some specifics. It's like, well, we want to do this to that using these variables or these arguments or these parameters. And again, this is all going to go within this call of a function, and the way that we think about these functions is they're just verbs, right? So these packages, they contain functions, they contain documentation, they contain data. So one package that we will dive deep into is a package called Applier. And Applier is a series of verbs that provide a consistent way of acting on data. And so here are 5 dplyr verbs. We're not going to get into them now, but again, I'll sort of interchangeably call them dplyr verbs and dplyr functions. And so we can do things like mutate, which is going to mutate a variable, or we can add a new variable. We can select. This is going to pick a column. We can filter. This is going to filter some of our rows, and so on. And all of these are just actions that we do to data. They're all functions. And a group of these functions, when we put them all together in a box, we call them a package. Okay? Now, I said that there are several of these packages. All of these packages, not all, most of these packages live within a place called the CRAN repository. And so you can go to this website here, and you can look and you can see all of the packages that are consistently maintained on CRAN. And you can go through and you can see that, this is just alphabetical, you can see that several different types of packages for several different types of activities. All right. Now, if we look at the number of packages ever published on CRAN, you can see it's a lot. It's a really sort of thriving and vibrant ecosystem that allows us to share. So we get a package, it allows us to do the thing that we want to do. Maybe eventually we can contribute to a package, we can correct something, we can write a function that will be eventually incorporated into another. The ethos of this community is to share. Everything is open, everything is shared, everything's available, and that's one of the things that I like most about this. If we are striving for this reproducibility initiative and having more rigor to our own workflows, having open source software and open packages that allow us to make these transformations to our data is absolutely required. And so this is just to give you a sense of the scope of what we're doing with, or what we're dealing with here. All right, now, in order to use a package, right? Okay, so it's great. They all exist. How is it going to help me? Well, we first have to install a package. So that's step 1. Now, one function within base R is install.packages. All right, this is quite intuitive, quite simple. The interesting thing is, this is going to download the files to your computer, and you do this one time for each computer. So if you want to, let's say, install a new package that you think is going to help with your analysis, you're going to do this one time, you'll download it, it will be on your computer. Maybe you'll have to update it. Okay, download it again, that will update it, and so on. But you do this one time. The packages that we will primarily be using for this Tidybiology course is from a collection of packages called the Tidyverse, hence the inspiration for the name Tidybiology, right? You were wondering where that came from. And so, so this Tidyverse is an ecosystem of R packages for data science that allows you to perform several different types of operations. So readr, for example, is one package that will allow us to take our data and read it into R. And then tidyr and dplyr allow us to transform our data and to clean our data. ggplot, which we'll be spending a lot of time with, is one of the primary packages that allows us to do and to perform data visualization. And there are several others. So we are using these packages that are sort of affinitively called the Tidyverse. All right, now, the Tidyverse contains the following packages. So if you wanted to install them, what would you do? Install.packages, parentheses, ggplot, dplyr, tidyr, reader, etc., and so on. Now, that's what it looks like. Well, hopefully we could cut and paste this. Or, even better, is that there's a shortcut called Tidyverse that serves and allows us to install and load the different components of the Tidyverse. So this is nice because what we can type now is install.packages, parentheses, Tidyverse, and this now will install a package in all of what you call dependencies. We'll install all of this group of packages so we can basically do this all at once because these different packages are designed to work together.
So Matt, how do you know whether there is a conglomerate that you can install versus having to go get bunches of individual packages?
Having a conglomerate, a group to install is rare. So almost in every simple case, which is the scope of what I know, you will install a single package and that will install its package.
Yeah.
The Tidyverse is designed to work together and therefore will install a group of packages. Now it turns out that actually installing the Tidyverse doesn't install every single component of the Tidyverse and installs a core set. So it's like nice and it's convenient, but this is absolutely rare. Because of the way that this is designed. Every other time you install one package, that package is there. Now, sometimes if you have a package that will require a function from another package, the package author will say, well, you need package A if you're going to install my package, because my package absolutely won't work unless you have package A. That's technically a dependency, so it will install that along with it. But when you start getting into unloading some of these packages, it will ask you about dependencies and updating and these things. So you might see some language about that. But yeah, this is the exception. Okay, now because you do this one time, I've already installed this into the RStudio Cloud environment for you, so you won't need to install this package now, or this series of packages. If you followed along on that install video to try to put this on your own computer, if you want to install a copy of RStudio locally, then you will have to install the packages also locally, and this is how you would do it. All right, now that's installing the packages. Step 2 is using the packages. And the way that we load the package, the way that we use it, is every single instance that we start an analysis, that we start a session of R, we need to load a package. All right, and the way that we do this is by saying library, parentheses, and the library that we want to install. Okay, so in this case, we can say library Tidybiology, and this is going to load, in the sort of rare case of Tidybiology, Tidybiology is one of the packages we'll use for this course. It will install the Tidybiology package. If we want to install the Tidyverse, the rare instance of the group of packages, we would say library, Tidyverse, etc. So this is now one time per R session. So most of the time that you will have something in the beginning of your code, in what we call a setup chunk of your R Markdown document, where we set up the stage, set up the environment for our analysis. And in there, we load all of our libraries. Because if you load a library, let's say in the console, and then you do some analysis and you write it in your R Markdown, and you go back to try to repeat that analysis, it will say, oh, we can't perform this function because this library isn't loaded. Now, it's a very easy fix. You just load the library. But so you'll see oftentimes in code, one of the first things you have to do is load the libraries. Okay, so when you load the Tidyverse, what you'll see is that it does the equivalent of these things. So again, it's a subset of the packages, and instead of all of them, these are the most common, sort of the core Tidyverse packages and functions that we'll be using for this course. Okay. So because we need to do this every single instance, I haven't done this for you. So if you want to run some analyses, you will then type library, parentheses, and then the packages that you want to start. So I just mentioned this concept of a setup chunk. So the setup chunk, so these code chunks are these gray chunks, right, that you were just running, has the code. A setup chunk is the very first chunk. It's always run once before everything else. If you call something setup, it will run this first. You put it at the head. And so you can see in this really small sort of fuzzy example that we have a setup chunk there, and we have there, a big stick. We have a setup chunk that has library, has Tidyverse, and this chunk is called, oh, there we go. I blew it up for you. Right, so we've got library, Tidyverse, and this is in this chunk that actually has a name that we call setup. So chunk labels are optional. You don't need one. If you put them in there, the one thing to keep in mind is that two chunks cannot have the same name. Each chunk has to be slightly different. Otherwise, when you try to run the analysis or knit the document, which we'll talk about a little bit later, it will break. So if you have a label, great, make it unique. The setup label is special. This is going to be where all of the information goes to set up the document. So now what I want you to do is go back to the exercise that you just did. If you ran the very last line of code, I think it was commented out, which means there was a little number sign in front of it, so it didn't run. But if you did run that last line of code, you should have gotten an error. The error says that we can't find this function. So the reason is because I didn't put a setup chunk in that document for you. So I want you to do that now. So go back to 1_exercise RMD. It's the same one that you were just looking at. And what I want you to do is I want you to have put a setup chunk there, and I want you to load the Tidyverse package. I want you to run that chunk, and then I want you to go all the way to the bottom of that R Markdown document. I want you to delete that little number sign, and then run that and see if it works. All right, so let's just take a minute to do that. I told you like 3 or 4 things there, so let me know if it wasn't clear. But what I want you to do is I want you to put in a new chunk here, and I want you to type library, Tidyverse, run that, and then go to the bottom. Okay. Now, I could take a moment just to mention to you right now, say, how do you install, or how do you put in a chunk? Lectures. Exercise. So this is the document here. Okay. So I want you to go somewhere here or even here. It doesn't really matter. But before this chunk, I want you to insert a new chunk. So what you can do is you can do that here by insert. You can do it here by insert, or there's the shortcut, which I would encourage you to all sort of force your fingers to learn. And then I want you to load the library. I've installed it for you, but I want you to load the library called Tidyverse, and then come down here, and this is the error that you would get. It says, I cannot find the function ggplot. Well, that's because we didn't load the library. So then I want you to delete this little hashtag right here, and then run this by clicking here and seeing if you can get a nice, beautiful plot. If you have a question, shoot your hand up, and Akshay, Ali, or I will come around.
Matt, while you're waiting for questions, can you take a question about the label, those label chunks? Or
Yeah.
whatever you call it? I've not seen that before. What's the advantage of having those? Does that only show up in your knitted document, or is there some purpose for getting in the habit of giving your chunks of code labels?
Yeah, so the question was about the benefits of giving your chunks labels. So it's all about the knitting process.
Okay.
So it doesn't, like when you run your code, I don't know of any benefits. When you when you knit a document, one of the default labels of the figures generated from that knitted document will take the name of that code chunk. So if you do have labels, then you will have some thought about what the image file names are that were generated from that code chunk, for example, if you didn't explicitly specify them. So I've learned that recently. And then also when you're knitting, if you're knitting a longer document, it will give you an idea of, rather than I'm knitting unnamed code chunk number 7, it will at least give you a sense of where you are in the process. But as far as some major utility, it probably appeals to like the type A in you to like want to have everything named. But as far as some major benefit, I haven't come across it yet.
This one.
Yeah,
We
those,
have to, like, where is that?
how do you do them?
Yeah.
Okay, so that symbolism is here. Yes. Now, we go over in class, also the shorthand. So you have to have this little curly bracket at the bar, but the simple way to insert a code chunk, so like let's
Is that this thing? Yeah.
And if you press Control, Alt, it does it. Which is easier than taking a
Control
whole
Alt
I for insert. Yep. But you'll want to do it in a Workspace. Insert code jump instead of right.
All right, now some of you saw that when you loaded the library, Tidyverse, that you had some warnings, some conflicts, maybe some error messages. Now, the basis for that's not something to worry about. What our studio is trying to tell you there is that if you have a package, and the package has a function called myAwesomeFunction, and then what happens is, let's say Allie made a package, and in her package, she has a function called myAwesomeFunction. So what happens is you can name your functions anything. These package authors get to decide what they want to name something. Now, if you have a package that has a function with one name, and you have another package with another function of the same name, then you'll have a conflict. All that means is that when you are writing your code, in order to use, you can use both of those functions because you've loaded both of those libraries. You've attached those packages to your workspace. What happens is you just need to specify. So the conflict message that you're getting is if you want to use, in this case, filter, you need to specify filters coming from Applier or filters coming from stats or wherever it was. So that's what that message was. Any other questions? All right. The power of R and the R ecosystem are these packages. It's the work that other people have done that they are more than happy to share in order to help other people do the things that they want to do. You know, in the biological sciences community, there are several labs that make amazing reagents and then put them on repositories like Adgene or some fly or worm stock databases, or that make the reagents that they made completely accessible to the community. That's exactly what's going on here, and it's great because it accelerates science and these processes. Okay, so the Tidyverse has this way of thinking and this way of analyzing where they have an import step. You import data in. They tidy the data, and that means a very specific thing in the context of the Tidyverse. They transform the data, visualize, model, transform, visualize, model, and basically go through this iterative process in order to try to gain some understanding of the data that was put in, and then finally communicate. So the reason that this process is outlined in this way is because there are different packages for each of these steps. So there's one package that will import, and another package that will tidy, and then another package will transform, visualize, model, etc., and communicate, and so on. And so we can think about these packages as discrete tools in our toolkit that allow us to perform a series of steps related to this process. All right. Now, in the field of statistics, there's a term that's called exploratory data analysis, which is a major concept and a major element of data science. And so the most colloquial and simple way to describe exploratory data analysis is to import a data set, to clean it up, and then to roll around in it a little bit, right? To really try to understand your data. And talking to any statistician, she or he will say the most important thing to do is to really understand your data. And are your data missing values? And are your data normally distributed? And are your data, all of these questions about the data, which really can only come from you rolling around in your data. So I think it's actually a pretty appropriate metaphor that we have this sort of cyclical and circular series of steps here, because this is the rolling around in the data to really try to understand it. So one of the main things that we will be doing in our time here together will be trying to teach you tools for exploratory data analysis. All right. Now, again, we're not going to go into the details today, but I'm trying to give you a sense of where we're going. So the import step has a package that is called reader. A lot of the R packages will end in the letter R. It's both cleverly named or usefully named, but perhaps now not so clever. But anyhow, this one's called read R. And we can read CSV, TSV, tab delimited files, or other delimited files, and so on. So these now are functions. The functions then are going to perform an action to an object. And in this case, we're going to read a CSV file in. Now we tidy and transform. So this is going to be two packages, both tidyr and Applier. And this is going to be, again, mutate, select, filter, summarize, arrange, some core verbs, core functions that we will be using to understand our data. We'll have an entire day devoted to Applier. We'll have another day devoted to ggplot. This is all things visualization. In fact, the power of ggplot is one of the reasons that the Tidyverse concept and that this R ecosystem is so strong, is because regardless of the other types of programming languages, people find the visualization tools in ggplot both simple, intuitive, and powerful that allow people to perform some analysis in some software, come over here into R, use ggplot to visualize, and back and forth. Now I'll just take a moment to mention that the R Studio can run both R, but also other software. So you, if you want, can use R Studio as an integrated developer environment for R, Python, and other programming languages, all within the same R Markdown document with different code chunks that specifically call the different software languages to use. All right, so we've got visualize, and then finally, we won't be able to spend much time on modeling. This is going to be far beyond the scope and time that we have here, but there's this both emerging and developing area within the Tidyverse for the modeling using a package in one case called Broom. Okay, now I want to introduce one of the most important and useful concepts within the Tidyverse, which is called the pipe. All right, does anybody speak French? Anybody know what this says? No? You're going to rely on my translation? All right, it says, this is not a pipe. Ceci n'est pas un pipe. All right? So this is a famous piece of art that was sort of quite popular, but it's also pretty tongue-in-cheek, right? So it says, this is not a pipe. And even from the back of the room, you'd say, well, yes, it is. I can see it's a pipe, right? But the painter said, well, no, this is not a pipe. You can't stuff it full of tobacco. You can't smoke it, and so on. And it's actually quite coincidental, but appropriate. We're talking about the names of things and talking about how we really try to know something and to how well we know it. And maybe some people would say we're parsing words here, but I would say that this is really appropriate. That this is one of the images that is named for an operation with an R that we'll be using quite a lot, which is called the pipe. So there's a package called Magritter, which is a package that was developed the concept of the pipe. And this is going to be heavily used in the Tidyverse. Okay, so this is a percent sign, and then a chevron, and a percent sign. Okay, now, this pipe, whenever we see it, we're going to pronounce it and then. So the whole concept of this pipe is to be able to pipe together a sequence of functions that sequentially apply to an object. So we're going to start with an object, and then we're going to do something to it, and then we're going to do something else to it, and so on. All right? So here's a simple example. So we'll go through it together. We wake up. Who do we wake up? We wake up self, and then we put on. What are we putting on? This is going to be like an argument, one of the specific things that we want to put on. We want to put on clothes, and then we're going to eat. Again, another argument. We are going to eat breakfast, and then we are going to go. And again, we can set an argument here. This is going to be where are we going to go? We are going to go to work. So this is a style of programming that's called literate programming, where this is pretty verbose, right? We've got a lot of text. We got a lot of things that are going on here, but it's really intuitive, right? You guys are like an hour into learning R, and this makes sense, right? Wake up, and then close, and then, and then, and then. All right. The alternative, which would be to write this in nested code, would look like this. Go, eat, put on, wake up, self, close, breakfast, 2 equals work. This is completely legitimate. It totally works, right? Sometimes I find myself writing nested code. Like, it's totally fine, right? Computer scientists, trained data scientists, often find this much more intuitive and familiar. This and then this pipe, this is the reason the Tidyverse is sort of popular and intuitive and a great, easy entry into this field of data science because of something simple like this, right? Because we can all vote, I won't make you, I think we could all vote, though, that the first one is more intuitive than the second one. And if the second one's more intuitive to you, then I'm going to guess that you were trained as a computer scientist, right? And so then you can be up here teaching. So, all right, now, what does this code do? Roughly the same thing, we would say, right? We wake up self, put on clothes, eat breakfast, something here, and then go to work, right? Now, we could pretty much assume or interpret the outcome of this line of code is going to be the same as the outcome of the other line of code, right? I mean, there could be something really, really important there that we don't understand. Any guesses of what this function is? What do you need to do after you eat breakfast but before you go to work? You need to find my keys. Yeah, right. So just like when you're learning a foreign language, right? Like you're reading over the menu or you're talking to somebody, you might not understand exactly everything that he or she said, but you can kind of get the gist of it. That's where you guys are today, is that I want you to not get hung up like, okay, it's this and this and this, and then like everything breaks down because I don't know what this is. Like, no, like just keep going and this will get easier. Okay? So you could assume in this case safely, but you can infer that the bottom line, the bottom sort of series of sequential codes is going to be similar to the top. Okay. Now, we can also take this string of operations and we can assign it to an object. So we could call this morning routine, right? Or we could take the outcome of this and we could call it morning routine. If we wanted to string all of these things together into a function, we'd make another function. We're not going to be doing that. But if we wanted to take the outcome of this and assign it, we could assign this to morning routine. Okay. Now, still thinking more about the pipe. What does this do? Take a moment to read it. We'll walk through it together. We're going to take chromosome. So this is a data set. This is one of the data sets that you actually just made a plot of. All right? And then, what are we doing here?
Pull those 3 columns.
Yes, we're pulling those 3 columns. So we're selecting 3 columns, ID, variations, and base pairs. And then, what do you think the next line does? It mutates. Good. But what do you think that actually means in this case? It changes something, right? Just like the Teenage Mutant Ninja Turtles, mutagen. Good. No? Reference just for me? Okay. So what do you think %var is equals variations divided by base pairs?
So it's making a new column by dividing variations column, each row of variations column by the same value in that row of the base pairs column.
Yes. So if you didn't hear Keith in the back, we are making a new column in this case. We're going to call it %variation, %var, and then it's going to equal variations divided by base pairs. So now we have something that's % variation because it's total number of variants divided by the total number of base pairs in each ID. Okay? And then, last line, what does that do? It arranges them, and in this case, in descending order. Exactly. Holy crap. You guys just read a bunch of R code, and literally, this is like day 1, right? But this is it, right? We're looking at code, and we try to figure out sort of what it means, right? And we might not understand exactly everything the first time, but we're starting to get these ideas sort of strung together. All right, now, What does the second one do? How is it different than the first one? What was that? Assign, you had it right, yeah?
Assigns it, is it an object?
It's an object, yeah. So we assign all of the outcome of that to an object. Right? Now, that object, so the first one, we just took chromosome. This was like a big data set, right? We can think of it like an Excel file. We'll call this a data frame now, though. So it's a big data frame. And we did this series of operations to it. So if we think about chromosome var, just it's our chromosome variation, how many columns will chromosome var have? 4. The 3 that we originally selected and the 4th one that we made. And all of this will be sort of beautiful and arranged by our percent variation, but arranged in descending order.
So mutate is a verb,
Mm-hmm.
right? So that makes a new column called mutate.
It makes a new column called percent var.
Okay, got it.
Yeah. So here's the thing, and we'll spend all day tomorrow on deployer verbs. This is a deployer verb. But here's the thing I'll tell you, is if you put mutate and you put in the name of a column that already exists, it will change that column. If you put in the name of a column that does not exist, it will create it for you. Okay? Keith?
But if you were to reverse that to mutate variation divided by base pairs equals percent var, that would generate gobbledygook?
Well, so when you write a function, you will, the package authors will tell you what arguments it's expecting in which order. And the way it works is mutate is expecting the name of the column first. Because then it's going to decide, am I making something new or am I going to change something? Okay? So all of the functions, and we'll get to this right at the end today, and we'll have some help documentation to tell you about the function and what it's expecting, and basically how to supply the information that it needs in order to function. Okay, so it turns out that this is what the percent variation looks like. So if we plot this, then we now have a plot where we've got the ID of our chromosome, and we've got the percent variation. And this is just sorted now by our chromosome number, but we'll talk about this more a little bit later. But this is a couple of lines of code to take 2 data sets, basically 2 columns, to compare them, to divide them by each other, to make a new column, and to plot it. Okay? So, last couple of things to finish up here. So, I would encourage you guys, I won't grade you on it, but I would encourage you guys to participate in the final project next Tuesday. So the final project is going to be a 2 to 3 minute oral presentation in front of your peers, which is going to be an opportunity for you to describe what you did to your data, present the output file, describe some observations, and then maybe what you would do to follow up on it. Okay? And we will set you up for success by teaching you all week, giving you some data sets, teaching you how to do this. But I would encourage you to do it. We will have a final project file that will be some analysis. This is actually the example of the analysis that I made. So I'll sort of show you all of the code for this a little bit later. But this would be an example of a final analysis. Like I took the chromosome data set. I was curious about the percent variation among the different chromosomes. And then it turns out that X and Y chromosomes have the lowest amount of variation. Isn't that interesting? All right, so I made all of this in R. I would sort of describe my thinking and maybe describe some ways to test it. Again, we'll talk about that a little bit more later. Now, a couple of things. Writing code is not like drawing an owl, right? So writing code is much more specific and straightforward. Writing code is much more like this. It's a stepwise process. Like if we think about where we're going, we want to build this house. But we know that we can't just build the house. We know that we've got to start with some foundation, and then we got to think about a door, and then we got to think about, right? So we think about these steps, and maybe then we've got some versions along the way where we can think, okay, well, now I've at least completed this. I might not know exactly what to do next, but I know that I have to get there, and right. So it's this stepwise process, and this is part of the reason to use our studio and to use our Markdown documents is because we can capture some of these ideas as we go through it. So a couple of resources I want to point you to, and then we'll just wrap up for today. So there are some cheat sheets, okay, within the RStudio Cloud. Over here, you can see there's cheat sheets on the left. If you click on that, it will give you a bunch of cheat sheets. If you are working in RStudio, what you can do is come up here to help cheat sheets, and you've got a bunch here. Now, it turns out that there's also Google. If you type in data import cheat sheet R, you will get the cheat sheet, right? There are like cheat sheets which are summaries of different functions that summarize transformation. So I just want you to know that these are available for you when you are writing code, when you're trying to figure out how to achieve some different transformations of your data. I use these all the time. In fact, I downloaded them on my computer. I have a shortcut because it's virtually impossible. Like one time I was on a flight and I was trying to work on a project, and like I couldn't because I wasn't connected to the internet and I didn't have my cheat sheets, right? So like you will find that there's a plethora of resources available to you. Okay, one major one that you will often find is Stack Overflow. So if you get an error message in R, you copy and paste that message into Google, like 9 times out of 10, it will bring you to a website called Stack Overflow. So Stack Overflow is a community of developers, programmers, that will help answer questions that people have. So you will find that there's other people have had that error, and people have already figured out how to overcome that error. Or for me, I always forget how to remove the legend title of a legend in ggplot, so I have to Google it every time. And then sure enough, like, you know, the number one question, remove legend title in ggplot comes up. And then Google is nice enough to remind me that I visited this page like 2 days ago, and I'll click on it and I'll remember what the code is, and I'll sort of write it in, or more likely cut and paste. Anyhow, Stack Overflow, also good resource to know and to have. Finally, there's a great book that's called R for Data Science that's freely available online at the website right up there. You can buy the book; it's like $20 or something, or it's not like some small version, chapter 1 or something. Like it's the whole book. So if you want a sort of formal, non-bootcamp, non-fire-hosed introduction to R for Data Science, this is like the Bible. This is like the book that people reference as a great intro place to start. Okay, now finally, there's something called help file documentation. So if you are in RStudio, you can type question mark and the name of a function. So go ahead and do that. Type question mark mean. And what you should see, so this is down in the console now. What you should see is that the some information comes up here. So if you're in the console, question mark mean. What happens is over on this side, a help document comes up. This is the arithmetic mean, description, usage, some arguments, and it tells you all about it. You can also search here. It's the same. If you type in this case, like, let me think of a good example. So ggplot. This is a function. The function is expecting data, some mappings. It will give you a bunch of examples here at the bottom. I found these examples really helpful because really what I want to know is like in which format is the function expecting the data, because there's no always consistent way. All right, so there's help functions there, and then lastly, you guys can hang out for like another 5 minutes if you want, or if you want to go get back to work or campus or wherever you need to go. There's one final document in the intro folder, which is called 01_homework. So I would encourage you to read through the file and the code and just try to do everything it tells you. So it shouldn't take very long. This isn't like, an hour of work or anything like that. So you can go ahead and do that now. If you hang out and do it now, Ali and Akshay and I will be around to help answer your questions. If you've got to take off, but you end up with questions later, you can go ahead and just post them on the Slack channel. We will do our best to help you. But that's what I have for today. So thank you for your time, for your attention. The plan is tomorrow, same time, same bat channel. Yes? No? Okay. So tomorrow is going to be all things Applier. We'll have some guest lectures this week by Ali and Akshay. I've been mentioning them. If you don't know, so Ali and Akshay are postdocs here in the DPI who are aficionados, experts, yeah, who have graciously agreed to help develop this course and to co-teach it. So they will be doing some guest lectures and also helping with some of the exercises. So thank you for your time today. Like I said, take as much time as you need here. There's nobody in this room immediately after. Otherwise, I'll see you tomorrow.